Okay, chapter 14 is about epoxides and ethers. Did you notice anything in particular about the slides? Yeah, there's like hardly any. That's our favoriteest thing about epoxides and ethers. They're super unreactive, which is why they get used as solvents and things, because they won't react with all this other stuff. So there's hardly anything to do. Woo-hoo. We've already opened the epoxides. Okay, one thing you can do with ethers, though, is if you use HBr or HI, you can cleave them by heating with concentrated HBr and HI. So if you had a reaction that you needed to add that HBr to, and you needed to heat it up for some reason, then you wouldn't use an ether as a salt. Okay, because of this whole issue. Okay. Okay, so when you do this, the first thing that happens is you protonate the oxygen of the ether. Okay? When you protonate, it's like, remember, the electrons are reaching out and plucking the hydrogen. Okay? They're like plucking it off. Y'all are still writing your arrows backwards. A lot of backward arrows. And there's a lot of non-arrows. You got to learn how to do it. We're going to do it the whole rest of the year. Think of it this way. Then you go to Bob Kim and you do it again. Okay? So you got to learn what these arrows mean. So we're going to reach out and pluck that hydrogen. And then the electrons in this bond go to the bromine. Okay, so what changed? Well, the electrons right here on the O, these two that I tried to make red and the pen refused, are now in this bond. Okay, so the O has now become positive. All right, then your halide will attack the carbon and displace the alcohol. Notice that the halide doesn't attack up here and you lose RO minus, because that's a strong base. Remember, good leaving groups are weak bases. All right, so this will attack the carbon next to the O, and then that will leave. So far, so good? Okay, what happens to the alcohol after? So you're going to, okay, so this is the alcohol that left. This is the alcohol that left on the previous slide. That's what that alcohol is. So what happens now? We're gonna protonate the O with HBr, because you can't tell the acid, don't protonate the alcohol that's formed. Just protonate the ether, okay? They don't listen. They protonate everything they can. Okay, so this O will reach out and grab that proton, just like we did, like reach out and pluck the proton up. All right, so that gives you okay, and then your alkyl halide will typically do an SN2 reaction and kick off water. Okay, so what ends up happening is that instead of just forming a alcohol and an alkyl halide, you form two alkyl halides. Okay, okay, now this right here. This, though, does not occur with aromatic alcohols or phenol. Okay, so if one side of your ether is directly attached to a benzene ring, okay, you would get this alcohol and the alkyl halide from the other piece. This will not do this, okay, because this carbon is what hybridization, first of all? SP who? SP2, okay? We don't do regular substitution reactions on SP2 hybridized carbon. Okay. All right, now let's see if we got some. Okay, so what are the major organic products for the reaction below and a mechanism to account for their formation? So first of all, can you tell me what the products are going to be? Here is your hint. So what will happen? You will protonate the O, and then what will happen? What will add? I minus, and it'll kick off an alcohol, okay? And then the other alcohol, the alcohol that's kicked off, then reacts with another equivalent of HI and makes another alkyl iodide. So you're going to get this one and that one. You're going to get two of them. The only time you don't get two of them is if one of them is phenol. It's the only time. All right, so here we've got HI. All right, so what happens first? One of these lone pairs goes and grabs the proton, and what happens to the electrons in this bond? Go to the I. Okay, there's a point right there on a mechanism. You protonate correctly. Okay. All right, so now that's going to give us, here is where we were. Okay. We didn't do anything with that lone pair, so I'm just going to put it back on there, more or less. All right, I'm making it. Okay, so what did we do, though? That O is now bonded to an H, right? And what else? And it's positive. Okay, and then what happened to the I? It has how many lone pairs now? 4, so it's negative. Okay, so now what happens? Where does the I minus go? It goes to the what? Where? What? Nope. It goes to the, yes, one of the carbons that the O is attached to so that it can get those electrons. Okay, so the O won't be positive. Is a tendency to always want to make the minus go to the plus, but it doesn't always get you somewhere. Okay, this now, this piece over here is a good leaving group. Okay, then what do we get? So now we're going to be at, we're going to have, okay, there's our alcohol that left, and we're going to add that other lone pair on there. Okay, so you see that the O is neutral now. Okay, and what did we get from the other side? The I attached to the propyl group. Okay, now what happened? It kind of does it again, where we protonate the alcohol. All right, I guess we're going to have to do this extensively. All right, so that's going to get us to, okay, here's what we didn't touch, but here's what we touched. So this O is going to have an H on it. And now it's going to have what charge on the O? Positive. Okay, and what else do we make? I minus. Okay, what does that I minus do? Uh-huh. And then you give that, the electrons in that bond back to the O. So that's how you get it. So you're going to end up with this plus 1. Okay, so that's how you get the two products. I guess this and this are your two products. See how we get them? So it's almost like you're doing the same mechanism 2 times, really. You're protonating and displacing. Protonating and displacing. Okay, substituting. What?
Is one matrix?
No, because it's one on each side. Yeah, so it doesn't matter which one you do first. Not really, but probably the primary one would be easiest, so it'll go first, probably. Okay, what if this one was tertiary and you got down to this part? Would it be like this? What kind of reaction is this when the halide comes in and the leading group leaves in one step? What? SN2, no SN2 on tertiary centers. No SN2. If you forgot that, write it down again. You okay? All right, so what are the products from this reaction? I got something. Is that it? Yeah. Okay, so 17. You see how often they clean. Okay, what happens first? Protonate the O. Then what? The bromide displaces. Okay, then what happens to the resulting alcohol that was formed in the leaving group? It gets protonated again and bromide displaces, so you end up getting this. You end up getting both of the bromides. You would not have, you wouldn't mix HBr and HI and try to get a bromide in it like that. It wouldn't work well. You see that? You would get all of the possibilities. It wouldn't be very good.
Does the excess have any effect on it?
Well, you have to have more than one equivalent.
Right.
If you have one equivalent, you'll get like this big mixture because some of it will have protonated the ethers and done the displacement, and some will have protonated the alcohol that was formed and done the displacement. So you're going to get a mix. So usually we use 2+ equivalents to make sure. Then what you would do at the end of the reaction is you would neutralize the excess HBr. So you'd probably add bicarb in there and stuff. Slowly, right? Did you learn that in lab yet? You have to add those two together. When you neutralize, you add them fast, it spews everywhere. You know, it's a little more exciting, but okay. Okay, remember when you do one with a phenyl, a benzene ring, okay, that what will happen here is you're going to do the same thing. You're going to protonate, okay, but then when the bromide comes in, it's going to come into this carbon and displace that alcohol, and then you're done, okay? Everybody see that? No further reaction. So you would get the alcohol and the alkyl halide from one like this. If you had phenyl-O-phenyl, it wouldn't react. But I'm not going to. You might do something else with the phenyl-O. Okay? So just remember, I just want to remind you of that. Okay. Here's your hint. HBr and HI convert both alkyl groups, but not aromatic. That's the benzene ring. I keep thinking we're going to get there. Groups of an ether to alkyl halides. Phenolic products are unreactive. That's how come. Okay, now, what if you had this one? I just want to make sure you got it. That one. Okay, we're going to add, let's stick with HBR. And I'll write excess. It doesn't mean extra small. Somebody said that once. Why does it say extra small on my test? And I went, oh, sorry, that's excess. Yeah. See, something weird like that asked me. I may have used a shorthand that I hadn't mentioned. All right, so what do you think you would get from this one? Any ideas? Okay, what now? CH what? What do you want me to write?
The ring and CH2 PR.
And what else? I wrote it the way you started to say it. Okay. So how come this one reacts? Because it's, okay, that's what I want to make sure you got. Okay? So you can see that it's got to be directly attached to the bin. Then otherwise it can still attach. Okay? Okay, predict the products for the reaction below. Can you read that, the structure? Can you read them? Do you need me to try to write over them? How about you guys in that? They're okay? I just hate that I paste my drawing program into this program, and that's how they come out. But it doesn't do that on Word, it doesn't do that on my other programs, it doesn't do that in PowerPoint, none. Just the Smart. Okay, then we're going to start chapter 15. Look at that, whole chapter in 20 minutes. Only they were all like that. I could do them all in 20 minutes. I'm like, dude, I could just be these fast. All right. Yay. Okay, notice that the OH is still on the benzene ring, and then this is the other piece. Okay? Do you see why it's not the? That's the kicker. Okay. All right, so now, I have to go back and go open the next thing, because I didn't try to make it. Uh-oh, this has writing on it. I forgot to check this file. Okay. Oh. Open. Okay, I'm looking at the other one. All right, chapter 15 is about conjugated systems, orbital symmetry, and UV-Vis. Okay, is that enough to confuse you already? Okay, what is conjugated system? Remembers what conjugation is. Are you telling me you slept?
No.
Okay, conjugated system is double, single, double. Okay, double, single, double. That's conjugation. Okay, so you remember we talked about dienes that you get conjugated double bonds. Okay, so guess what we're going to talk about in this chapter? What reaction? Diels-Alder, woohoo! Another one of my favorites. You know what that means? Okay, orbital symmetry. Okay, we're just going to do the basics of it. Okay, but it's going to have to do with the pi electrons in a conjugated system. Okay, and then UV-Vis. What do you know anything about ultraviolet spectrum? Did you not do a little bit in Gen Chem? Like, did you not take little things and put little cuvettes in a little thing and look at it? What are those? They have a special name, those things you use in Georgetown.
I remember Smith.
I can't remember what they were called.
Something to do with some color. Yeah.
It might have changed color.
It was like neon.
Okay. We did use, well, there's a box where you put it in, you use a wavelength. Yeah. Okay. But we also used ultraviolet light when we did TLCs. Right? Did you do TLCs and look at them with ultraviolet light? Okay. What happens is the ultraviolet light is causing an electron to jump. And this is why things get colored, because it's easier for them to jump. Electron to jump to a higher energy level and relax back down. So that's what the UV does part is. That's going to be like 2 slides. There's hardly anything. Okay, so conjugated. Double, single, double. That's conjugated. Okay, isolated. You would have to have more than one single bond between them. More than one. You could just, well, you can't have one, then it's conjugated. But you could have 2, 3, 4, 5, 55. Okay. Cumulated. That means that they're next to each other. Okay, that's a little bit different. Yeah, those are all the 3 possibilities. There aren't any of them. Okay. Okay, identify the structure with the isolated double bonds. Which one has isolated double bonds? They all have how many carbons? Except for E. E doesn't have 5 double bonds. It has probably many. Many carbons and many double bonds. Yeah, you might have to kind of draw some of them and look at them. Okay. Woohoo! What kind is the first one? What kind of double bonds are those? Cumulated. All right. How about the next one? What are those? Conjugated. No, they're all complicated. That's what this one is. Complicated. What is D? Amen. Okay. That one was out. Okay. All right. So in the Diels-Alder reaction, we're going to take a diene and we're going to add a dienophile. Have you heard those terms? Unfortunately. Okay. What characteristic do you think a diene has? What characteristic does a diene have? A conjugated what? Double bonds. Yeah. Okay. Conjugated double bonds. It is important that it have conjugated double bonds. If it doesn't, it ain't gonna work. Okay, a dienophile is something that is diene. What does phile mean? Greek philosophy. Greek people. What?
Love.
Love. Yeah. Greek diene loving. Phile is loving. What in Greek is not like? Go. Okay, so this is diene loving. Okay, and you'll notice that I have the simplest dienophile that you can have and the simplest diene that you can have. Okay, so I got a diene plus dienophile. You have to have in your dienophile pi electrons, or it won't. Okay, so you must have pi electrons. You notice down here it says that the mechanism is concerted. What does that mean? One step all at the same time. Woohoo! Okay, and what is the 4 plus 2 cycloaddition? That is the pi system. This has 4 pi electrons, and this one has 2. That's how we get 4 plus 2. Okay, now, you ready for the mechanism? I'm going to take that and go there, that and go there, and that and go there. And it does it all at once. It makes that noise too. Did you listen when you did yours, or were you talking? You probably were talking too loud and you didn't hear the molecule go. Did you do the one that's really super fast in the little valves that I wrote? You did that one, didn't you? You just shook it up and you were like, hey, it's done. I like that one. It's really cool. Okay, now I want you to notice where these 2 carbons are over there. They're the ones that have the double bond on them. And what else did we do? We made some new single bonds, didn't we? We made this one, this one. Okay, so every time you do this, you make a 6-membered ring with a double bond, aka a cyclohexene. Okay, now you can have a whole bunches of stuff out here, which is the exciting part of the reaction. Okay, so here's the mechanism. This time I drew it the other way. Notice that last time I picked clockwise and this time I picked counterclockwise. Does it matter? No. What matters is that they all are going clockwise or counterclockwise, your error. Okay? Okay, so up here I drew the transition state. Notice that in the transition state, we're making this bond, breaking this bond, making this double bond, breaking this double bond, making this single bond, breaking that double bond. So that's how come it's like all the way around, the little partial bonds. There aren't any changes in pluses and minuses. Okay? All right, this is called a pericyclic reaction. Did Dr. Zhang that? Okay, it is a reaction that proceeds through a cyclic transition state, aka our cyclic transition. Okay, now I keep saying this syn addition. Remember what syn stood for in addition? Same side. Syn is same side. That's going to matter. Okay, that we're adding from same side. Okay, let's look at some. They're so cool. All right. Oh, we get to do one. Okay, here we go. I want you to do that one. You can do it. Figure out what you did. So you're going to have to draw it and then name it probably. Right, how you I need a little more caffeine. I'll draw the mechanism up there after we. I got 16. Shouldn't I have 17? If nothing else, y'all make a choice. Because a guess is better than no choice. Always. Okay. So we're going to go here, here, and here. So we're going to make that what you got? Probably drawing a little nicer. Okay, so how do you name that? 4-ethylcyclohexene. Right, remember the double bond is carbons 1 and 2. Okay, so that's why it's not 3-ethylcyclohexene. Gosh, I didn't even give you that choice, did I? I'm getting slack in my old age. Okay, so what makes something a good dienophile? Good dienophiles are electron loving. Okay, they want electrons. So if you put an electron withdrawing group on the carbon double bond, that makes it more reactive. It will react faster. That's what you had when you did your reaction in the lab. That's one of the reasons why it went really fast. Okay, so notice what's on here. Electronegative atoms, carbonyl, nitrocyanide. And you can do the reaction with a triple bond. Ooh. So let's say that you had this plus this. What would you get? We're going to do the exact same reaction. So we're going to go like this. So what would you make? I'm going to do it like this. Okay, so now our new parts are, we have a bond from here to here, right? And a bond from here to here. And over here we have a double bond. But look at what we made. A 6-membered ring with 2 double bonds. That's because we started with a triple. So you can do the reaction with a triple bond. Okay, notice what didn't react. This double bond, because it's a carbon. Okay, it didn't get to go to the party. Kind of like the whole neighbors thing. Okay, so you're going to look electronegative atoms you want on your dienophile. All right, so here's one. One is similar to the one that we had, but a little bit different. Okay, and I have a double bond there. Okay, and notice over here that you can't read very well. Worked on my other thing. Benzene 100 degrees C. That's a pretty standard way of running these. You just heat them in benzene and they go pretty quick. Okay, now the easiest way to figure them out is to redraw them. So you see how I redrew it over here so that I've got my diene and my dienophile. Okay, anybody have problems picking out the diene and the dienophile? Good on that? Good. All right, so go over here, do your little mechanism, and then figure out what the product is. The easiest way to do it. Okay, got to start at the beginning. All right, so I'm going to go. All right, so I'm going to get that. Everybody see where the pieces are? Okay, can you pick out the new carbon-carbon single bonds that were here and here? That's real important to be able to do that because you know we're now you're already scared. Oh my gosh, look at this one. Does that look familiar? That's what you used in lab, was that dienophile. Okay, and once again, 100 degrees C, benzene. You didn't even have to heat yours. It just went at room temperature. Okay, so do you see how I redrew it? Okay, now all of a sudden it looks more complicated. Didn't the thing you made in lab look really complicated? Didn't you have like all these benzene rings and stuff? And it was like, whoa, okay. Because you can make really complicated things really quickly. One step. This got used to make a whole bunch of compounds that had 6-membered rings in them, of course, but they were used as insecticides. Like all of a sudden they made like 50 new insecticides. Some of them were very good. They didn't know that until they started using them and figured it out. All right, so is this what you got? Everybody see that? Wow, we got 2 rings fused now. Cool, don't worry about naming it. Just worry about drawing it. Okay, so this was our new bond, and this was our new bond. Okay, ready for the next one? All right, how about this one? This time I didn't write it out for you, the little picture. I'm making you write your own little picture. Do you sense a theme in the condition? Okay, so redraw it and then write it out. See if you can take those molecules and put them like I've been putting them for you. You don't have to use the sticks. You can do it the other way. That's okay. Isn't Diels-Alder kind of fun? Caden's like, no. So this is what I'm going to do. I'm going to do it like this. And then you have to figure out over there what part reacts. What do you think ET stands for? No, ET stands for ethyl. I don't use it very much. Okay, so is that what you did? You could have written it out more and written all that other stuff. Oops, I'm going to kind of go like that. I think that looks better. Okay, so what did you get? Did you get? Pen quit on me. Did you get that? No, you got this, right? 2 double bonds. Okay, because you had an alkyne for your dienophile. Okay. Nifty-galifty. Okay, what about the dienes? We talked a lot about dienophiles. The dienes prefer an S-cis conformation. Okay, so here is an example of the S-cis conformation. What we're talking about is rotating around that single bond. You can't rotate around double bonds, but you can rotate around single bonds. So you could have your molecule in this configuration on the right or in the one on the left. If it's in the one on the right, it won't react. What will happen is it'll wait until it swings around, because remember the molecules are moving, until it gets boom, S-cis. And you got your double bonds lined up like that. Okay, then it reacts. It reacts. Okay, so that's called the S-cis. You probably have never heard of those little terms before, and this is the only time. Okay, so look at this compound. This compound up here on the left cannot become S-cis. You see that? Because of the ring structure. It's stuck like that. This one will not react in a Diels-Alder reaction. They like made that compound and tested it just fine. Okay? But this compound up here is super reactive because it's stuck in that S-cis conformation because of its ring structure. So you see the difference? Okay? It's so reactive that it reacts with itself. So what does that look like? So here is our compound. So it's got to be the diene and the dienophile both if it's going to react with itself. Okay? So that means we're going to react with one of these double bonds. Okay? So we're going to go there, there, there. Can you draw what you get? That's the hardest part sometimes, is drawing the structure. Okay, so do you see where you're getting the six-membered ring from? Okay, so that's going to be from okay, there's your six-membered ring. So what else is attached to those two carbons? I'll make it. Okay, so that's, oh, this pen. There's that. See, that's the left side. And then over here is the rest. Okay. That's pretty complicated looking. That's the what structure? Remember talking about bicyclo structure? Yes. That's probably like a tricycle. Don't worry, we ain't going to name it. Okay, so what happens is this is so reactive that when you have cyclopentadiene, which is what that's called, cyclopenta, I'm running out of room, diene, cyclopentadiene in a bottle, it exists as this. It exists as this. That's what it is in the bottle. You cannot tell the molecule, hey, don't react with yourself. Okay, I don't care if you're super reactive, don't do it. Okay, you could put it in the fridge, you can cool it down, it'll still do it. Cannot stop. So what if you wanted to use that to do a Diels-Alder reaction? Well, what is nifty about Diels-Alder reactions is they will also go backwards. That's called a retro Diels-Alder. And so what you have to do is, it's called cracking. You heat it to a really high temperature and you distill it off as it's being formed, and then you would use it. Now, a couple things about that. Number one, don't use a Bunsen burner. We did that once and somebody lit it on fire. Number two, it smells. It has an awful smell to it. It's not bad like a skunk smell. It's just, look. Okay, I think we all had headaches. Anyway, we didn't do that again. But if you had to do it, because that's your research, that's what you're going to do. But you would take that and you would heat it, and you would actually use a fractionating column to do a fractional distillation.
And then we got like you would shake it and it would turn yellow, or the other way.
No. You used two solids. If you did the one that I wrote, and it was real complicated looking, you used two solids, I don't think. And it was real small amounts because the one is real expensive. That's how come. So if you do this one, this is a liquid, and you have to crack it. Okay. No, but you put the toluene in, it looks cool. Yeah, you probably did that part. All right. So here is a Diels-Alder reaction. Okay. And I'll see if I can't find the movie for us before we go. Okay. Draw the arrows for this. It's just written sideways. Okay, see how we got that? Okay, let me see if I can find it. I forgot I needed to find the movie. So are y'all ready for the break? Okay, you realize I'm writing lines all over my yellow. Look at that. All right, go away. Okay. Movies. Diels-Alder Movie. There it is. I bet that's it. Oh, we have to convert it first, y'all. Did Jay-Z show you? Did not? Cool. All right, so let me see if I can make it bigger. Green, the green, thank you. Usually there's something else that I. Here it is. Wow.
Yeah.
It went so fast that we didn't see anything. I'm like sad. What happened? Let's try this one. This one says empty floor. Oh, this is the one with the loads. Okay, so before I start it, do you see these are the pi electrons? Remember, they're above and below. Okay. All right. There's going to be more pi electrons. Here it comes in. Now look at there. All at once. Okay, got it? One more time. Here it comes. Pi electrons. We're making those single bonds. And notice that back here, you form the double bond. That's why I drew it sideways, because the video was sideways. All right, one more time. Watch the double bond forming in the back. That's pretty. It's kind of like blowing bubbles. It's popping bubbles. Okay, so we're going to do some more Diels-Alder and work our way backwards. So we're going to start with the start product and figure out what to starting material with. Oh, yeah. Fun, fun. That's a nice little problem.